Welcome students to the new topic called as consolidation test. In the last class we have seen about the consolidation plots, and in that consolidation plot I told you that this plot we will be getting during the consolidation test. So this consolidation test is outlined in IS 2720 part 15 1965. So this test is outlined in this particular IS code part, and by doing this test what we will be getting is the coefficient of the consolidation. This is our aim, and this coefficient of consolidation we will be applying it to the practical field. Like suppose we know the coefficient of consolidation value, right? So by knowing this particular consolidation value, we know the relationship between CV and TV and CV, which is TV equal to CVT divided by D square. So for a particular degree of the consolidation, how much time the clay will take in order to consolidate up to that particular level of degree of consolidation, that time you will be getting once you get to know about the coefficient of consolidation value. So what happens is that in practical case, if you got the clay which is sandwiched in between the drainage layers, so let's suppose this is the drainage layer, this is also, so, and let's consider this as the rock. So if the compressible layer is compressed, so what we will be doing, we will be taking a sample at a particular depth, and then we will be testing this particular sample in the lab, and by testing as per this particular code we will be getting this particular value, that is nothing but the coefficient of consolidation. So we'll go with this procedure, but prior to the procedure I would like to highlight some of the formulations. Like we have seen, by deriving the one-dimensional consolidation equation, we have seen that the K equals to CV MV into gamma W, and what we will be assuming that the K and MV value will not change during the progress of the test, and since the MV and K value will not be changing during the progress of the test, so CV is also assumed to be not changing during the consolidation stage. So CV will remaining it as a constant. During consolidation test. Okay, so that's what I would like to highlight, that CV is remaining constant. CV is not changing or varying, increasing or decreasing during this particular consolidation test. So we have got the apparatus or the setup for this particular consolidation test as per IS 2720 code, and I will get back to this particular setup. So this particular consolidation test is carried in two different ways. One is a floating ring test and another one is a fixed ring test. So what happens, the difference between this particular floating and fixed ring test is as follows. In floating ring test, the sample is squeezed or compressed from both the ends, while in fixed ring test the bottom part of the sample is kept constant. Also bottom part is not allowed to be compressed, only the compression will be taking place from the top side direction. So in floating ring test the sample is compressing from both the sides, while in fixed ring test the sample is not compressing from bottom, it is only compressing from the top. So I'll write it over here. Sample is compressing from both the ends, and for the fixed ring test the sample is only compressing from top. sample is compressing only from the top in case of the fixed ring test. Since the friction which is developed on the sides of the wall or the sides of the container with the sample, so for that it is essential to draw the diagram or the lab setup diagram. We have got the container which has rigid boundaries. This is particular the container, and the soil is placed inside the container, and the porous stones are also placed to the top and the bottom of the soil. So this is the soil, these are the porous stones, and this particular sample is kept in an assembly, and this particular is the porous stone. So this is the porous stone, this is also the porous stone at top and the bottom, and this is the loading cap through which the concentrated load is distributed over the soil area. So this is the loading cap, and the whole assembly is kept submerged under the water. Remember, in case of the fixed ring test, since this sample is squeezing from only the top, the water whatever will be coming out from the bottom can be measured, and as well as the amount of the water can be controlled. So therefore all the permeability measurements can be done only in the fixed ring test. This is very important point. So the K value can be measured and as well as controlled. Measured and controlled only in fixed ring test. Since the sample is squeezing from both the ends, you will not be accurately calculating or get to know about the amount of the water can be gone outside of the soil specimen. But in fixed ring test, since the top part only getting compressed, from the bottom whatever amount of the water coming out, which can be measured and as well as that can be controlled in fixed ring test. But the only advantage of having the floating ring test is that the friction which is developed along with the borders of the container and the soil is minimum in fixed floating ring test. So therefore it minimizes the amount of the stress concentration on the edges which is happening during the application of the load. Since the very negligible amount of water is there onto the top of it, so whatever the change in the effective stress will happen will be because of the applied load divided by the total area. But for the total area calculation, you must have the dimensions of the soil specimen. So this dimension of the soil specimen are as follows. The soil typically in this case have the diameter ranging from 65 millimeter to 110 millimeter, and as per as thickness is considered, the thickness of the soil specimen varies in between 15 millimeter to 30 millimeter. Remember, the ratio of the diameter to thickness is kept in between 2.5 to 5. 2.5 to 5. This is as per IS 2720 part code. This is as per the procedure is as per the Indian standard codes. And what you will be doing, I've shown you the test setup. So once you have placed the soil, so what you will be doing, you will be placing just the load, and you will be calculating the deformation through the dial gauge. And dial gauge is sensitive, it is very sensitive to the deformations. So once you place the load, so load also has to be placed like this way, to 0, 25, 50, 100, 200, 400 and 800. kilonewton per meter square. So like this is the loading arrangement, and by this amount you will be placing the load onto a soil, and correspondingly you will be noting the final deformation, or you will be noting final dial gauge reading, I'll call, which is the representative of the strain. Strain is nothing but the decrease in the height to the initial or original height h0, or the height I will call it as by the thickness. Height or thickness is one and the same, denoted by h. So this is the I call it as the axial strain versus this is the axial stress response you will get. This test is very famous. So what you will be getting? You will be getting the strain values or the dial gauge reading after each increment of the load. But remember, every load has to be placed to a minimum 24 hours. So this load has to be, each load, I'll write it over here, each load has to be kept for at least 24 hours. So this is also as per the Indian standard 2720 code part 15th. And by doing all this test, you will be getting the axial strain versus the stress response, and I'll call it as the dial gauge versus the pressure increment. I'll call delta sigma dash. This is the dial gauge. This is the dial gauge versus the stress increment response. That's what you will be getting by doing this particular test. And also, if you notice this particular graph, the initially while you are applying load, the soil will be getting compressed with very less amount of the time, in small amount of the time, and then after that it will be compressed like this way, and then this is the loading part. And once this is loaded, you will be removing the load, you will be unloading it. Since the soil is not elastic, it will not go and hit to the initial part, it will go and hit to the some other part, and then from that you will be again compressing. So this is the again recompression, and then this will be the virgin compression. This is the virgin compression part, that the soil is first we seen this, therefore the name virgin came. And this part is the expansion part. Here you can place the dial gauge reading or the void ratio. Anyway, both are the representatives of the same. So this is the expansion part and this is the recompression part. And based on the slope of the virgin compression curve, we have defined the compression index, which is Cc, slope of the virgin compression, slope of the recompression curve denoted by the Cr, and slope of the expansion curve we call it as swelling part, that is Cs, slope of the swelling part of the curve. But apart from this particular curve, as I have discussed you with in the earlier classes, that you will be getting the curves which is representative of the dial gauge reading versus the time. I'll take it as the dial gauge reading. So at a suppose particular value of the 25 kPa, at the 24th hour you will be getting one dial gauge reading, and as the test is slowly progressing, you will be getting the consistent amount of this curve. And if you place this particular dial gauge reading versus the time in the logarithmic plot, you will get a curve of S shaped like this. You'll get the curve of S shaped, and if you place the this is a particular logarithmic of the time, but if you place the y by keeping y ordinate as the same, just x ordinate is changed, rather than time I'll be placing square root of the time. So then you will get the curve which is most likely to be like kind of an exponential curve, like this one you will get. So as time goes on, your dial gauge reading goes on increasing. So remember, here it's a 0, and this is increasing progressively like this way, dial gauge reading, right? So from here also it is again increasing progressively from top, otherwise it could be an in the reverse way. And so and in this particular case, y-axis is again the same, dial gauge reading. And based on this particular consolidation curve, this particular curve is more emphasized by the Casagrande. And he emphasized this curve, and from this curve, he told a procedure to calculate the coefficient of the consolidation. He told about the graphical procedure, I am calling it as. And also from this curve, Taylor is more emphasized, and he again given the graphical procedure in order to calculate the coefficient of the consolidation of the soil. And these are the two procedures by which you can calculate the coefficient of the consolidation, which is the final outcome of the consolidation test. But apart from this coefficient of consolidation, I would like to have the one more clarity about the E versus P curve, because which is very important. See, we have in earlier stage also I have drawn this particular EP curve. Just the EP curve. See, in many cases the curve would be like this way. So if the curve is like this, it is not easy for you to determine the recompression part and the virgin compression part easily. And then you will follow the Casagrande procedure in order to find out the point corresponding to the pre-consolidation pressure. And by that procedure, what you will be doing? You will be finding out the point which has the maximum curvature or the minimum radius, and from that you will be drawing the one horizontal straight line, and you will be drawing a tangent line to the curve, and you will be bisecting the angle made by the tangent with the horizontal, and you will be extending the straight line part to backward, and it will meet to this particular angle bisector at this point, and the stress corresponding to this point we will be calling it as pre-consolidation stress, or I'll call it as the sigma C dash. And therefore we will be recognizing that this part will be the recompression part and this part will be the virgin compression part. But this procedure is given by the Casagrande, and we see in this particular procedure. But what happens in many cases, because of the you will be taking the sample in the field and you will be testing it in a lab, so there are the disturbances and there is a loss of moisture and there is a kind of a remolding effect that the sample will experience, because of which the curve will become like this. And for this such kinds of the curve, it is not easy for you to determine that from where the pre-consolidation stress is locating. So for such kinds of curves where it is not easy to find out the breakup between the recompression and the virgin compression part, the Smartman gave the smart procedure to locate this particular point where it is equal to the pre-consolidation stress. And as far as his procedure is concerned, he have divided the procedure into two parts. One part is applicable to the normally consolidated soil and one part is applicable for the over consolidated or the pre-consolidated soils. So for the normally consolidated soils, which means the existing stress is equal to the pre-consolidation stress, for that he tested n number of the sample and he came to conclusion that the whatever you have got the initial void ratio, this particular field curve and the laboratory or the theoretical curve will meet at the point where the void ratio is 42% of the initial void ratio. So this particular part would be the point where both the curves will meet. and from this point, if the line is drawn which is tangent to this particular curve, so this will become like a virgin compression part. And from this virgin compression part, you need to just place the value of sigma O, because you have imposing the present stress exactly equal to the pre-consolidation stress. So you need to find out the sigma dash, and you need to extend it to the forward side direction, and it will again meet to this particular point, and you need to draw a horizontal line like this. So you'll be getting this particular recompression part of this curve. So you can get the field curve like this way. This is straight line, and this is the field curve, right? And this is applicable for normally consolidated soils, but for over consolidated soils, you see, if you have the curve like this, which is a continuous kind, you cannot get the two different parts like virgin recompression and the virgin compression part. For that, this is for the over or pre-consolidated soils, one and the same. Over or pre-consolidated, one and the same meaning. For this particular part, what you need to have is the as I said earlier, this is the initial void ratio, and we'll be taking 0.42 or 42% of the initial void ratio, and we'll be drawing a straight line. And wherever it meets, you need to draw a tangent line. You need to draw a tangent line. And I think this procedure is I guess the same. So there would not be any kind of the change in this process. But remember, if you have unloaded this particular specimen in the lab, then it would follow the path like this. This is the expansion part, and then again you will be recompressing it, so there would be a recompression part. So this would be the recompression part, and then again if you have loaded from this particular point, then again you will get the virgin compression part. So this particular part is the recompression part. Recompression part. And since it's for the over consolidated soil, you know how much amount of the stress you are imposing now, so you need to mark this particular stress value, and you need to draw a parallel line from this particular stress value, because it's meeting to this particular laboratory curve. So you need to draw the parallel line from this point, which is parallel to the recompression part. So this line is parallel to recompression part, and the slope of which is the CR, that is recompression index. So this is the parallel line drawn to the recompression part. So this becomes our field curve from this particular sigma O dash. This is present stress. This becomes your field curve. And the computations on the settlement is done on the field curve, not on the lab curve. And this particular method, we call it as the Smartman method. He has given this name. The method of this is Smartman field extrapolation method, and whatever you will be doing the calculation on the settlement, as far as settlement part is concerned, we'll be doing it in the field curve, not in the lab curve. You need to transfer the lab curve into the field curve in order to have a good correlation in between those. And therefore this finishes the consolidation test. And in the next class we will move ahead with the determination of the coefficient of the consolidation from the Casagrande and the Taylor's method. Thank you.